Before I ended the last video, I started talking about the equilibrium of three non-parallel coplanar forces. That is, three forces are in equilibrium and that they are non-parallel, but they are coplanar. Coplanar forces act on the same plane. We also have forces that act on the same line, along the straight line. We call them collinear forces. Then we have concurrent forces. These forces act at a point on a plane. Now we are dealing with the case of three forces in equilibrium. And then we say that the system is in a state of static equilibrium. And I said that we can use what they call triangle of forces in equilibrium to represent the three forces. And the three forces will be taken in order. And I drew one last video that when you have this case now, the three forces are acting in a way that they follow each other. You can see that the weight of the body acts vertically downwards, and that is reflected here. The horizontal force this way, that's reflected in this diagram here, and the tension in the string acts in this way, directed at an angle theta degrees with the vertical, and that's my force T. And then the forces must follow each other. And I said again that the resultant of any two of the three forces must be equal to an opposite to a third force. That's to show a system in equilibrium. And that triangle must form a closed figure, a closed shape, a closed triangle to show that the system is in equilibrium. And when they don't form a closed figure like this case, now when it is drawn like this, that is a resultant force that acts. The system is not in equilibrium. The body will eventually move, accelerate in the direction of the resultant force. Okay, we continue from there in this video. We're looking at the equilibrium of three non-parallel forces again in a more detailed manner. Now, I already said that when these three forces are in equilibrium, number one, the lines of action of the three forces must meet at a point. You can see that now at a point, if you trace this other tension down, into the beyond this way or beyond this point, this level here, it is meeting at this point. That shows that the three forces, one, two, three, can meet at a point. So that if I'm taking moment, what is moment? The product of force and the perpendicular distance measured from that point to a line of action of the force. So when I have, let me just redraw the diagram briefly here. So let's say this is my force H acting at this point, the weight of the body at the same point, and force T at the same point. So if I take the moment of any of the three forces, let's say moment of H about this point O, where the object is, where the three forces are acting, the moment of force H gives me 0. Moment of H about point O gives me 0 because there's no perpendicular distance measured from the line. This is the action. And then the one thing about moment is that when a force, the moment of a force is taken about the same point that force is acting, the moment is equal to 0. Okay, so again, I said that for this same system equilibrium, the moment of, okay, I've said that already, then the sum of the resolved forces acting along any direction, I think I mentioned this in my last video, must be equal to 0. We can decide to resolve one of the three forces. Of course, this force H is acting horizontally, it has no vertical component. Mg, the weight of the bulb, is acting vertically, it has no horizontal component. But this force T, the tension in the string, can be resolved into its horizontal component, which is a component of T acting along this line, along this x direction, in the negative x direction. And this force T also has a vertical component acting along the positive y direction. Okay, so what are these two components? I can use my SOHCAHTOA, with the angle, with the head of this angle, and this is my adjacent, and with the head of this right angle triangle, I can say this is my opposite over hypotenuse, that is sine. So my sine theta gives me opposite. Maybe I can call this one x over hypotenuse, that is t. So my force x is equal to t sine theta. So I can replace this, my s, with t sine theta. That is a component of force t that is acting along the negative x direction. And if I resolve vertically, I'm resolving along this line, that is adjacent over hypotenuse. So that is I can call this my y. That is my y. It would now be equal to what? That is t cosine theta degrees. That is cos theta is y over t. So that's the component acting along the y direction, t cos theta. Now, for this system to be in equilibrium, once again, I said the sum of the resolved forces acting along any direction, whether it's along the vertical x-axis, the vertical direction, y-axis, or along the x-axis, the sum of the forces must be equal to 0. That means that it means that force H, I can decide to give this positive. Any force acting to the right along the positive x-axis, call that positive. This acting along the negative x direction, I can give that negative. So that H minus T sine theta, what I'm trying to say is that this sum of these two forces, H plus minus T sine theta, or simply H minus T sine theta, must give us 0. And resolving along the y-axis, that is to say, if I give this vertical direction, the downward direction positive, then the upward direction I take it as negative. It also means that mg minus t cos theta must be equal to 0 for equilibrium of the system. The sum of the resolved forces along any one direction must be equal to 0. Now, maybe I should just take an example. How do we solve for this? Maybe for some they can give this case, given that the mass of the bulb, let's say you are given that the mass of the pendulum bulb is, let's say, 300 grams. We have to calculate the tension in the string, and the horizontal force that was used to pull that pendulum bulb from this point to this point. Of course, given that the tension makes the thread or the string makes angle 30 degrees with the vertical. Sometimes they can give you the angle it makes with the horizontal, so you should be very, very careful there to know what exactly to do. So let me redraw my diagram. So using my triangle of vectors, I can use that to solve it, or I can use the one I just resolved just now to also try to solve for the two forces H and the T. But let's use this one first of all. Now this is my force T acting along this line. This is my theta 30 degrees. Angle makes with vertical. This is my 30, the weight of the body, of course I have to look for that. And then this is my force H, okay? This is my right angle. Now, what do we do here? First of all, I have to convert the mass of the body to its weight, since T and H are different types of force, So the weight of the body is mg. The mass 300 grams will be changed to kilogram. That is 0.3 divided by 1000. Multiplied by, let me take g as 10 to simplify my calculation. That gives me 3 Newton. That is the weight of the block of the bulb. Okay, so quickly, I can use my SOHCAHTOA. Opposite over adjacent, that is a tangent. Tangent is opposite side, the ratio of the opposite to the adjacent side, okay? That's tan theta now, gives me h over w, which is 3 Newton. Okay, so that h is equal to 3 tan 30. And if I use my special angle expression, I can say tan 30 is 1 over root 3. That gives me 3 over root 3. I can rationalize 3 over root 3. If I rationalize that using my rationalizing denominator, I have 3 over root 3 multiplied by root 3 over root 3. That gives me 3 root 3 divided by 3. 3 cancel 3, that gives me root 3 Newton. I can expand that. Root 3 is about 1.73 something. So that is the value of force H. How do I find force T? Can you use the same SOHCAHTOA? This one, let me use adjacent to hypotenuse. That is cos 30 now is equal to adjacent, which is W, over hypotenuse, which is T. So which means that my W, my T, is equal to the weight, which is 3 Newton, divided by cos 30. And what is my cos 30? Cos 30, so that T equals 3. What's my cos 30? Root 3 over 2. This 2 goes up. That gives me 6 over root 3, which I can rationalize to give me 6 root 3 over 3. That is 2 root 3. That is my first T. Okay, that's one way of solving this question using SOHCAHTOA. When you are given the weight of the bulb or the mass of the bulb, you see how we got the weight from it, and from there we quickly found the value of force T and force H. Okay, quickly, let's try to look at or use this other equation to solve it. We can use that to, the sum of the forces acting along any of the directions, whether along the y-axis, y direction, or along the x direction, must be equal to 0. So if I use the second equation, mg minus t cos theta is equal to 0. Mg is 3 Newton, that is the weight of the bulb, minus t cos theta is my 30 degrees, is equal to 0. It means that t is equal to 3 over cos theta, which we got that time. And then to get the second equation, I can use the first equation to get the value of h, and that is h minus t sine theta is equal to 0. And that gives me what? Okay, h is equal to minus, that becomes t sine theta. When I bring the sine theta to this side, it becomes t sine theta. So that my force h is equal to t, which was 3 over what is that again? Cos 30 times sin 30. Of course, cos 30, ratio cos 30 sin 30. Sin 30 cos 30 is tan 30, so h is equal to 3 tan 30. Okay, so that need to you can complete that by evaluating the 3 tan 30. Okay, so what we're saying is that when three forces are in equilibrium, we can use triangle of forces to tend to resolve these forces, that is to find any of the values of the forces given. We can find the forces that are unknown, okay, if at least one of them is given. Now, the second principle or theorems I'm going to use now is called the Lami's theorem. The Lami's theorem too can be used to resolve or to find the forces, in equilibrium for a system under the action of three forces, three non-parallel coplanar forces. We can use Lami's theorem. Okay, let's see this case now before I state the theorem. Let's say you are given three forces in equilibrium. We have a body that is hung by means of two different strings, okay? One of them is attached to this point on the ceiling, and that one, by means of this thread, is attached to this point. And let's say the body of mass is at this point. Oh, of course, the weight of the body acts this way. Okay, so I can call this force in this tension in this string P. I can call this one Q. What I call the weight of the body acting at point O, W. Okay, so let's call the angle here between P and Q alpha degrees. Let's call the angle between P and W beta degrees. And let's call the angle between Q and W gamma degrees. Okay, so Lami's theory says that the ratio of one of the forces, let's say force P, over the angle between two forces, the ratio of this force to the sine of the angle between the other two forces, which is which is sine gamma, is equal to force Q, ratio of force Q, to the sine of the angle between the other two forces P and W, that is sine beta, and is still equal to the ratio of force W, which is the weight of the body, to the sine of the angle between the other two forces, that is sine alpha. I'm sure you got it. This is my force P. Lami's theory says that this force P now, the ratio of it to, now these other two forces, they have an angle between them. That's angle gamma. So Lami's theory says if you take this force P over the sine of this angle is equal to force Q over the sine that is of the angle subtended by these two lines. That is these two other force lines. Okay, and then I'll also take W over the sine of the angle alpha, which is the angle between the other two forces P and Q. That does not mean we use the three expressions, because in solving equations, solving problem mathematics, we don't use two equal to sign. It's only one we use, depending on the parameters given. Because here we have four parameters, P, Q, for instance, gamma, and beta. So which means if I'm going to find angle beta, or I'm to find Q, for instance, I'm given beta, gamma, and force P. That will enable me to use these two terms of this equation to find the unknown, which is Q, thereabout. Okay, we can also translate this with triangle of forces, because in some cases, if you don't want to use it directly, you can also translate the triangle of forces. Or before then, let's take an example. Giving this example quickly, let's say you have this system of forces, and then the question will be very specific here, that the system is in a state of equilibrium, static equilibrium, under the action of these forces. Okay, let's say this is my force, whatever that. Okay, let's say this is force Q, and force Q is 10 Newton. Force P is not given, and then they give you force W is not even given to, and they say this angle is 140 degrees, for instance, and this angle is let's say 160 degrees, then this angle is 60 degrees. If you add these three angles, sum of angles at a point, of course, gives you 360. 140 plus 160, that's 300, plus 60 gives you 360. Sum of the three forces, acting along at this point must be 360 degrees. Okay, how do we use Lami's theorem to find the value of the unknown force P and force W? That is the weight of the body W. Okay, since I have that, I want to find P first. I can say P over the sine. Which angle I want to use here? Is it 160, 140, 60? Of course, that would be 140. Sine of angle 140. That is, that's the angle between the other two vectors, the other two forces, equal to. Then this other one must be known. I'm giving a 10, which is this value of the force here. The angle between these other two forces is 60. That's 10 over sine 60. Okay, that gives me, making this be the subject of the equation. I have 10 sine 140, of course, divided by 1 by sine 160. Okay, you can evaluate that for me quickly because of time. That gives me 18.79. So that is roughly 18.8 Newton. We can do same to find the value of W. Okay, now I was talking about translating this to a triangle of forces. First of all, I need to draw the weight line. Let me start with that. The weight line acts vertically downwards. If I'm to use vector means or scale drawing method, then I have to choose a scale. After finding the value of force W, that is the magnitude of force W, the force P, and then this 10, I would scale them down. I can choose a scale of 1 to 1 if the values are not too large, or I can use the scale of 1 is to 2 Newton. Okay. All right, so the weight line acts vertically downwards. Now, if I'm to translate this to a triangle of forces, how do I represent the different angles? And these angles, 140, 160, and 60, are all external angles. They are going to form the external angles of the triangle. Please take note, not internal angles, not interior angles. They are forming the exterior angles of the triangle. Okay, so you can see that for speed, the weight is acting just like this. I'll draw this, which means my force P must act this way. This must be force P, not Q, because you can see the way force P acts, just like detaching this line, just as it is, without changing the orientation. And I place it like this, against this force, the weight of the body W. And then force Q is acting in this direction. So just as it is, I must draw my force P parallel to. So this line must be drawn parallel to force Q without altering the orientation of force Q. Okay, parallel to what I have here. That is taking the triangle or the sides in order, the forces in order. Now let's see the 140. 140 is the external force. Sorry, external angle between the weight and 10 Newton, which is my force Q. My force Q is given as 10 Newton. Okay, I call this my 10 Newton force Q. Okay. All right, so I'm going to draw this and extend this one, extend it like this, so that this is my 140 degrees. The angle between my, what is that again? The weight line and force Q, which is the 10 Newton force. Then the 160 is the angle between force P and the weight line. So I may like to extend this weight line vertically upwards still. And then this is my 160 degrees, the angle between the weight line, which is vertical, and force P, 160 degrees. All right, and my 60 degrees is the angle between the exterior angle between force P and my 10 Newton, which is force Q. Okay, so how do I represent that? My 60 degrees must be this one here. This is my 60 degrees. Recall I told you that all these angles are all exterior angles. They're not interior. They're not interior. Okay, by using the straight angle, sum of angles on the straight line theorem, straight angle theorem, this must be 20 degrees because the sum of this angle and this other one must give 180 degrees. Sum of angles on a straight line. This must give me 40 degrees, so that this plus this gives me 180, and this must give me 120 degrees. Let's confirm the sum of 40, 20, and 120. Does it give 180? Because the sum of the three angles, 40 plus 20 plus 120, must be equal to 180, which means the triangles, the angles of a triangle must add up to 180 degrees. So this is how we can translate something given like this to a triangle of forces, so that you can decide to use it. Since this is a right angle triangle, I can decide to use my cosine formula or sine formula in solving this. So I can go ahead to still use my Lami's theorem. So if I'm to use sine rule here, for instance, because sine rule can also be used. If I'm to use sine rule here, what do I do? Sine rule states that this ratio, just like Lami's theorem, W over sine, the angle that is subtended, of course, this side W subtends angle 120. Okay, that is the angle that is opposite this side. So that is sine 120 is equal to, I can say Q over sine. This side Q, the angle it subtends is 20, subtends angle 20 degrees. And then my side P subtends angle 40 degrees. You can see that this angle is opposite this side P. Okay, so side P subtends angle what? 40 degrees. That is equal to P over sine 40 degrees. So that does not mean we use all the three terms of this equation. Of course, this has two equal to signs. We don't use the two equal to signs in solving problem to choose just one of them. You can just choose any two to find at least one of them must be known, or one of them must be unknown rather, and all three must be known before we can use this equation. So this is how to solve problems on triangle of three forces. Okay, maybe we should look at one more question before I wrap up this topic. Okay, quickly we'll look at these three examples. You can see some systems here that are in the state of equilibrium under the action of three forces. You got a lamp, this kind of a sitting room lamp. You can see that it's held and suspended by means of two strings. One is attached to a point here, and there's tension T1 acting, and the other one is acting or suspended from this other point. You can see the lamp. The weight of the lamp is 10 Newton. And this one, they give us the angle it makes with the horizontal, that is for T1, makes an 30 degrees with the horizontal. So how do we find the values of T1 and T2 very quickly? We can use a triangle of forces to resolve this, or I can even use the idea of resolving forces. I can resolve that T1. T1 has two components. The component of T1 acting horizontally, of course, that is T1 cos 30. If you use your Sukatwa to resolve this, I've taught how to resolve forces in one of my video lessons. So if you're having difficulty, you can quickly make reference to that video, how to resolve a force into two perpendicular components. Then the component of T1 acting vertically, we call that T1 sine theta. Okay, for equilibrium, I told you that the sum of the forces acting along any one direction must be zero. That is T1 cos 30, because theta is 30, must be equal to T2. Okay, so since both forces are not known, let me use the vertical resolution. And some of the forces acting vertically must also be zero, meaning that the weight of the body, which is 10 Newton, must be equal to T sine or T1 sine theta or sine 30. So since this is given as 10 Newton, it means this is my T1 sine 30. Sine 30 is 0.5. That is 0.5 T1 is equal to 10 Newton. That means that T1 equals 10 over 0.5, and that gives me what? 20 Newton. So that is the value of T1. I can from there make substitution in this equation and find T2. Of course, T2 here is equal to T1, which is 10 cos 30. Cos 30 is root 3 over 2 or 0.866 as the case may be. That will give me 2 here. That gives me 5 root 3. Because of time, you can quickly use your calculator to find the actual value of T2. Okay, look at this second question here. There's a body here acting at point O. I mean, a body at point O under the action of these three forces. But to find the values of force P and force H, I can at the same time, just as I did the first one, I can equally resolve force P into its vertical component, which is component acting along this line. And that's my P sine 30. Of course, that's going to be negative. And this is P cos 30. Okay, for equilibrium of this system, it means that 10 Newton, the upward force, must equal the downward force, P cos P sine 30. This 0.5 P is equal to 10, which means P is equal to what? 20 Newton. And you can use the other, the forces acting horizontally to find force H. What's my force H? H must be equal to what? P cos 30. Since I've already got the value of P, that is 20 cos 30, that gives me the value of H. So whichever which way, you should be able to apply the ideas of either resolving forces or triangular to find the unknown forces. And look at this case of a picture that is hanging on the wall by means of a string that passes over a nail. There's a nail here. And then we have to find the tension T1 and T2 in the string. I can see that the angle between each string is not the same, that is between the string and the horizontal. And if I'm to use triangle of forces here to translate this picture, the system of forces into three forces, into a triangle of forces, the weight line always acting vertical downward. That is my 8 Newton. And then what's my T1? T1 is acting this way. So I'm going to, okay, that's my T2, sorry. I'll bring it like this. Place it against this line and draw. Just the way it is acting. That is representing it in taking the triangle or taking the angles in order. This is my T2. So T2 acts this way. I must draw my T2 parallel to what it is here. And then T1 acts this way. So I'll detach this or draw this my side of the triangle such that the orientation is the same as how T1 is acting on that picture frame. So this is my T1. And you can note clearly here, that the forces follow each other. T2 follows T1, the 8 follows T2, and T1 follows the 8 force, okay? Which is the weight of the body. Now let's see these three, something else. Now this angle 40, some students may just make the mistake of placing 40 degrees here and say this is 40 degrees, because here you can see that this is angle that T1 has, and then they quickly go and place 40. If we put 40 here, that will be wrong. This 40 degrees is the angle between T1 and the horizontal. Define this angle here. This angle here is the angle between T1 and the vertical. T1. So I won't put, if I put 40 here, that will be capital 0. I'll be completely and totally wrong. So what do I put there? That this angle will be 50 degrees. How is it 50? Come back here now. You can see that the angle that is required there is the one that T1 makes with the vertical. The vertical is the weight line. So the weight line can be drawn. Any vertical that line here represents can also be seen as a weight line, because the weight line acts vertically downwards. So I'm looking for this angle that T1 makes with the vertical line, because the weight is in the vertical direction. So this is still the weight line. So this angle here is the angle between T1 and the vertical. Okay, so that is, if this is 40, this will be 50, because the whole of this gives me a right angle, which is 90 degrees. 50 plus 40 gives 90. So what I need here is 50, and I'm sure you'll be able to know what angle this angle will be. That will be 38 degrees. That is, to subtract 90 from 52, or subtract 52 from 90, that gives you 38 degrees. And then this other angle, going by the sum of angles of a triangle, they must add up to 180 degrees. That gives me this angle between T1 and T2 is 180 minus the sum of 50 and 38. Okay, so that gives me 180 minus 88 degrees. So what is 180 minus 88 degrees? 180 minus 88 degrees gives me my angle 92 degrees, which is the angle between T1 and T2. Now this is a scalene triangle. We can't use SOHCAHTOA here. I can use sine rule or cosine rule to find the unknown T1 and T2. So maybe I can use the sine rule. Let's say T1 over sine 38. Okay, because T1 subtends this angle 38 is equal to the weight is 8, which is known, over sine 92. So with this I can find my T1, which is equal to what? 8 times sine 38 divided by what? Sine 92. So you can use your calculator to quickly evaluate that for me, and that gives you the answer. And to find T2, I can equally use 8 over sine 92 is equal to T2, because that was T1 I found first, over the angle between that, or opposite that side, is 50 degrees and 50. So that T2 gives me what? T2 gives me 8 sine 50 divided by sine 92. You can finish that up with your calculator. So this is how we find or solve the three questions involving three angles or three forces in equilibrium. Next video I shall move to the equilibrium of parallel forces. I'll start by talking about the moment of a force about a point. Thank you for watching. So do subscribe and share, and tell your friends about these video lessons, because I'll take time to analyze all the different aspects of physics topic by topic.